Let's continue talking about how we can describe quantitative data with numbers. So in the previous video, we talked about mean and standard deviation. Before we get into interquartile range and the 5-number summary and box plots, we're going to dive a little bit deeper into standard deviation and then also talk about range. So a couple of properties about standard deviation which are very important. We need to know that S sub x, which represents standard deviation for some variable x, okay, that value is always going to be greater than or equal to 0. Your standard deviation is only going to equal 0 when all of the values in a distribution are the same. So for example, if you were to go into a classroom of 3-year-olds at a daycare, and you were to take the standard deviation of the ages of all the 3-year-olds, well, everybody is 3. There is no variation, so the standard deviation there would be 0. Now, larger values of your standard deviation indicate greater variation, okay? Example of this, if you were to take the standard deviation of all of the ages of people in a classroom, right, the teacher included, if you were to do it with the teacher involved as far as the age and then also without the teacher, when you do the standard deviation with the teacher's age, it's going to be larger because there's a greater variation. Now, the standard deviation is not a resistant measure of variability, right? That means that it's going to be more sensitive to things that are extreme, okay? That's because it uses the squared deviations, so that makes it more sensitive to the mean, to extreme values in a distribution. There are going to be measures of variability that are more resistant than standard deviation, which we will talk about in the next video. Finally, standard deviation measures variation about the mean. So it should only be used when the mean is chosen as the measure of center. So if you're using median to describe your center, you wouldn't use standard deviation to describe your spread or your variability. You would use something else. Let's dive into that standard deviation formula a little bit deeper. If you will recall, the standard deviation formula is under a square root, right? It is the square root of the sum of the deviations squared, and then that's divided by n minus 1, okay? So we're talking about the population and sample standard deviations here, and then I'll talk about more just the sample one in a bit. So the reason that we square each deviation, and by deviation I mean each data value subtracted from the mean, we square them because we want to make them all positive. If we didn't do that, when you added them all, since some are negative and some are positive, it would sum up to 0. So we want to square it to make everything positive. So then we square root it because since we squared each deviation, we're going to undo that process so you can return to the original unit of measurement. For example, if you were finding the standard deviation of heights, okay, if you didn't square root it, it would be the number that you calculate for standard deviation would be your variance, and that would be, inches squared, for instance, or like feet squared, whatever you're measuring your height in. So you square root it to get back to the original units of measurement. The units of measurement for standard deviation is going to be whatever the units of measurement are for each data entry. So if you're doing inches for height, or pounds for weight, or number of students, if you're counting average number of students or something. Now, this is a little bit more complex, so stick with me here. Why do we divide by n minus 1 for sample standard deviation? Well, the standard deviation we are calculating is just going to be an estimate of that true standard deviation, right? That's why we use S as opposed to sigma. And remember, standard deviation is the average distance of all of the values in the population R from the mean of the population. Now, because we don't know the true mean, mu, we can't calculate the deviations from mu. So we use the mean of the sample, which we call x bar. Now, because x bar is the exact balancing point of the data will almost always be closer to your x bar, your average, on average than they will be to the population mean. So the sum of the squared deviations from your sample mean is going to underestimate the sum of the squared deviations from mu. Okay? In order to correct this, we divide by a slightly smaller number when you're finding the average. So that's why we divide by n minus 1 instead of n. So just realize that it's going to be an underestimate. That's the key part there. Now, why are we even bothering with variance? That's before you square root it. If you're only going to need standard deviation to describe variability. When we get to a later chapter and we're going to be putting multiple random variables together, you're going to have to use variance in those formulas and calculations and not standard deviation. So we do care about the squared standard deviation, which we also call the variance. Another measure of variability is the range. The range of a distribution is going to be the distance between the minimum value and the maximum value. So it's the difference if you were to subtract maximum minus minimum. So as an example, here are the data on a number of goals scored in 20 games played by the 2016 U.S. women's soccer team. And you can see those 20 numbers there. So to calculate the range, you find the biggest number. In this data set, the biggest number is 10. And then you subtract the smallest number, which in this case is 1. So 10 minus 1 is 9. So the range is 9 goals. Biggest thing that students mess up here. They think range, you would say, oh, the range is from 1 to 10. No. The range is a single number, okay? Just like standard deviation, range is also not a resistant measure of variability. It's affected greatly by outliers or a skew because it accounts for both the minimum and the maximum. So range is not good if your data is skewed or if your data has an outlier. So if you're trying to find a measure of variability that is resistant to those, you would want to use something like the interquartile range, which we'll discuss in the next video.